Dear all, welcome to our last recitation. Today we will solve questions related to applications of this course. Let me share the screen. Okay. Recitation 8. So problem 1. So problem 1 is related to Arcelor-Ascoli theorem. Prove that the closure of an equicontinuous subset is also so a solution. Let's E be here. I need to use the bounded functions on X because I will use the metric. I mean, I can write, I cannot write. If you write this, the continuous functions only if I take this set, then the supremum may be unbounded. So instead of continuous functions, I am choosing bounded ones, but E is equicontinuous subset of bounded functions on X. Be an equicontinuous subset. Let F be in here. Okay. Then there exists Fn. There's a sequence in E such that Fn converges to F in the submetric. So it means given any epsilon greater than 0, there exists an n0 in N such that the sub Fn F less than epsilon for all n greater than n0. We may write this epsilon over 2. So now we, as Fn sequence in this equicontinuous there exists delta greater than 0 such that if the metric xy is less than delta, then for all n in N, y less than epsilon. Okay. Observe that fx minus fy less than or equal to fx minus f sub nx plus so fny minus fy. Now this is less than or equal to So the first guy is less than d sub f and f, and the last guy is similarly less than d sub. So 2 times d sub f and f plus so we conclude that implies so for all n greater than n0 we have what? Fx minus Fy. So less than or equal to these 2d sub f sub n f plus this guy. So, and this is less than 2 times epsilon over 2 plus epsilon. So if delta is 2 epsilon implies if dxy is less than delta, we have two epsilon. Therefore, so delta depends on epsilon regardless of function f. So therefore, this closure is equicontinuous. Okay. In the beginning, we assume E is equicontinuous, so E closure must be equicontinuous. Okay, problem 2. Let Fm be bounded sequence in the continuous function on 0, 1, and so Gn define it like this. R be defined by so Gnx is so integral 0 to x, so fmt dt. So let me pass the second page. Prove that there is a subsequence of Gn which converges uniformly to a continuous function so solution. Let A be defined like this, Fn n, and define E as Gn n. These both are subset of the continuous function on 0, 1. Now, so x equals to 0, 1 compact set, compact, then if S is, so let me make some recall first. Okay. So recall this. Let X be compact set and S be subset of here. This set continuous function on X. Then, so S is compact if and only if S is bounded, closed, and equicontinuous. Closed and equicontinuous. Continuous. And this is a characterization of compact subset of closed functions on X. So this comes from Arzelà-Ascoli theorem. Now we will show that one needs to show, okay, A. Our aim show that A closure is bounded, is closed. This one is clear because I'm taking the closure, clear. And E closure is equicontinuous. So then I will say that this E closure is compact, but Gn is a sequence in E closure. It means Gn has a subsequence which converts to a function in E closure. It means that's a continuous function and belongs to here, this set, Cx. Note that E is, not E, this set called X is clearly compact as bounded plus closed subsets of R real numbers. Now, in the question, Fn is bounded implies there exists R greater than 0 such that A contains all Fn contained in B sub this ball. 0 is the zero function, is a zero function. May say closed ball. Or open ball is not so important. Okay, so what about Gn? So absolute Gn, X, let's say Gnx. This implies one more thing, the sub F0, Fn0 is what? Supremum Fnx, x in 0, 1, less than or equal to R. Okay, so in fact we will show that Gn is a bounded sequence, therefore our set E is bounded, hence E closure is bounded. But how? So we know Gnx equals to, so integral 0 to x Fnx dx, but this is less than or equal to 0 to x Fnx dx, sorry, not x, is a t, not x, sorry, t. Okay, but clearly this is less than or equal to 0 to x dt times supremum fn t in 0, 1 et. This supremum is a constant, some constant number, hence we have, this is, okay, so to x dt times d sup fn 0. So this is a x times d sup fn 0, but this is less than or equal to x times r, but x is less than or equal to 1 implies r. Therefore, this set, in fact, Gn is bounded sequence, implies R. So bounded sequence implies is bounded set. Then E closure is contained from here. Okay, ball, sup is a closed ball. Here, take the closure of both sides, but this closed ball is already closed. We have E closure. In fact, is in here. Implies E closure is bounded. But clearly, E closure is closed. So one needs to show only E closure is equicontinuous. But by problem number one, only must show our set E is equicontinuous. Okay, so, but how I will show? Okay, so given epsilon greater than 0 and for all xy in x 0 1, observe that. So gnx minus gny, any function of any element of E is some gn, so I can write like this. But what is this? 0 to x fn t dt minus 0 to y fn t dt. So we can write this like by integral properties, like dt, isn't it? Yes. So this is less than or equal to y to x. One more thing, absolute value, maybe y greater than x. So fn t dt, but as one may clearly observe, so this is less than or equal to yx supremum fn t in 0 1, here absolute value, dt, but here this is less than or equal to, so yx dt times r. This is equal to x minus y r. So we conclude that this ether is Lipschitz continuous. So choose delta epsilon over r. Then if dxy less than delta is this, then for all n, gn of x minus gn of y less than what? R times x minus y. Here, this metric is absolute metric, and this is less than r times epsilon over r, which is epsilon, implies E is a continuous subset of continuous functions on x. Continuous. Again, by problem 1, equal raise by problem number 1. From here, implies equal raise compact. Therefore, there exists subsequence gkn of gn such that gkn converges to g in a closure. Therefore, in here, as gn is sequence in our compact set E closure. So we are done. Do you have any question? Problem 2. Now we will solve a question related to contracting mapping theorem. Problem 3. Prove that there exists a unique bounded continuous real valued function f1x, but x is this, real numbers, such that f satisfies the integral equation. dt for all s in s. For all s in x, positive real, non-negative real numbers. Okay, solution. Okay, so let A be this set. Cx intersection Bx. So Y is set of continuous bounded real valued functions. Okay. Then Y d sub. This time the submetric exists is a complete metric space. Complete metric space. Okay. Define function theta from y to y as theta. So takes the f and sends 1 plus 0 to s. Yes. E to the power minus t squared fst dt. Okay. Let me check the question. Yes. Okay. And dt. So claim. Our claim is theta is contracted mapping. Mapping, which will imply theta has a unique fixed point. So then we will know. Okay. How theta is contracting mapping? I need to find some positive number between 1 and 0. So that's, let me show. Theta f minus given any fg in y. What is this? Okay. So 1 cancels 0 to s. dt. Okay. So this is less than or equal to 0 to s. Okay, absolute fst minus gst dt. Again, this is less than or equal to supremum. I will use 2 times sup 0 s. Here one more supremum fst gst st in x so dt. Here all things are positive. Here this to supremum s is an x. Okay, but clearly, so this x is 0 infinity closed interval. So we can write this thing as supremum. So ft as s times t trace this closed interval 0 infinity, then t only itself trace gt t in 0 infinity. As okay, as you observe, e to the power minus t squared is increased. So not as s increases, this integral is increases as we have super. Let me write the one more thing. 0 to s t times supremum ft t 0 infinity. The insight here, this integral as s increases, which is an increasing function because e to the power minus t squared is a positive function. So this guy's equals to, 0 to infinity minus t squared dt. In fact, this is a convergent improper integral, and the last guy is sub f g. Okay. So let me note how to calculate this thing. 0 infinity implies alpha square. So alpha square can be written like this double integral. Hop, dt du. This thing. Okay, so and the integral with respect to t does not relate to integral and does not independent to u, and similarly integral with respect to u does not depend on t. I can write the multiplication like this. So how to calculate? Use polar coordinates. What is it? Polar coordinates t a cos theta. So let's say a r sin theta. Then this thing becomes what? 0 to pi over 2, 0 to infinity, r dr d theta. If you calculate this, it becomes pi over 4, implies alpha equals to so at the end we have, so let me here correct something. Here we say here s and s, whole thing is function of s. Okay, so we conclude that for all s in x, this thing theta fs minus theta g of s less than or equal to, so alpha times t sub f g. This is true to for all s, in fact implies d sub theta f theta g less than or equal to alpha d sub f g. So here for some alpha with m1 implies theta is contracting mapping on complete metric space, y implies theta has a unique fixed point. So we are done. Do you have any question? So This is a problem 3. This was a problem 3, but about the problem 4. Let this sequence be an equicontinuous sequence in Cx, where X is not necessarily compact, we have some function, real valued function for some f(x) to r. We have what? So limit f(x) is fx. This is a pointwise for all x in x. Then show in fact f is a continuous function. Now, as fn be a continuous sequence in Cx, given epsilon greater than 0, there exists delta such that for all n in n, fnx minus fny less than epsilon whenever dxy is less than delta. Okay? As fn is equicontinuous sequence. Okay, so limit fnx is fx and limit fny equals to fy implies limit fnx minus fny equals to fx minus fy. And by limit rules, we have this equality. But this function, absolute value function, here to here, is continuous. We have limit n goes to infinity, absolute value of this sequence is absolute value of, goes to absolute value of fx minus fy. Okay. So, by with above delta, fx here, no need. Fx minus fy absolute equals to limit n goes to infinity of fnx minus fny. But these things less than epsilon as dxy less than delta implies this is less than epsilon. So from here, so we have fx minus fy less than or equal to epsilon, but this is less than 2 epsilon. Note that epsilon is arbitrarily positive number. 2 epsilon is not so important. You may choose 2 epsilon whenever dxy is less than delta. Implies f is continuous, in fact uniformly. Okay, Do you have any question? Is the problem? Sorry, problem 4. So we come to problem 5. Problem 5. Let X be a compact metric space. And let Fn be an equicontinuous sequence in Cx, and this is a complete metric space as X is compact. Assume that there exists some F element here and some dense subset A of X such that limit f1x fx holds for all x in A. Show that our Fn converges uniformly to F. Here. Okay. So, solution. First, we will show these two things, okay? Limit, in fact, Fnx is Fx for all x in X, not only in A, also in X. Second, we will show that limit Fn is F, okay? This is the first, and this is the second. So, okay, for all x and x, there exists sequence an in A such that an goes to x as A closure is x. We know A is dense subset is given, so its closure must be x. Good. Okay. So first, now, as fix some epsilon greater than 0. Now observe that as Fn is equicontinuous sequence, there exists delta 1 greater than 0 such that if dxy is less than delta 1, then Fnx minus Fny less than epsilon over 4 for all n greater than n0. No. As equicontinuous for all n. This is true for all n. Sorry. Okay, but the second observation, as f is continuous on compact set X, we have there exists delta 2 greater than 0 such that fx minus fy less than, say, epsilon 4 whenever whenever the xy, distance between xy less than delta 2. Now let delta the minimum of delta 1 and delta 2. Okay. So, şimdi for above delta, as am goes to x, there exists m0 in n such that the am x less than delta for all m greater than or equal to m0. Then one more thing. So what about this guy? Fnx minus fx. This is less than or equal to fnx minus fn am fn am minus fam. Oh, sorry. Let me pass the next page. Next page. Fnx minus fx less than or equal to fnx minus fn am absolute plus fn am fam plus one more things fam minus fx. Okay. Observe it. Okay, observe. Now, then, for all m greater than m0, we have what? Fnx minus fx less than or equal to epsilon over 4. Sorry, one more step. So, so let me write like this. Fnx minus fnam less than epsilon over 4 as the xam less than delta. And observe that fam minus fx. Also, this is less than epsilon over 4 as the xam less than delta. Now, in particular, we have fnx minus fx is less than epsilon over 2 plus, in particular, am0 fam 0. But as limit fn am0 is fam0, there exists l0 in n such that for all m greater than n0, sorry, less than epsilon over 4 implies all n greater than n0 so from here we have limit fnx is fx for all x and x. Now again, now we will show fn f uniformly. As x is compact and greater than 0, there exists x1, xk in x such that compact means paracompact and delta is greater than 0. So we have x is union I1 to k, both xi delta. So our epsilon in the beginning, fixed epsilon, as the limit fn xc x sub e is fxi, there exists n sub I in n such that for all n greater than ne, fn xi minus fxi less than epsilon over 4. Let n0 be maximum of ni, I equals to 1 to k. Then clearly, for all n greater than n0, fn xi minus fxi less than epsilon over 4 for I equals to 1 to k. Okay? So then, fnx minus fx less than or equal to fn x minus fn xi plus fn xi fxi, one more sum, fxi minus fx. For sum. Why? Because x belongs to x, it means this x belongs to some. This x belongs to some ball xa delta ball. So I conclude this guy. Then, and for all n greater than n0. Then say less than, here less than epsilon over 4. Why? So these things, dxxi less than delta plus the second one, limit fn xi is fxi. Sorry. The last thing, dx delta. Fn equicontinuous. Here f is uniformly continuous. This is less than 3 epsilon over 4. So we conclude what here implies for all n greater than n0. For all x and x, we have fnx minus fx less than 3 epsilon over 4 implies d sub fnf less than or equal to maybe, but this is less than epsilon. Implies for all n greater than n0. So we are done. Fn converges to f uniformly. This is problem 5. Do you have any question? No. Let me solve some questions related to Bayer category theorem. Problem 6. If X is complete, metric space, which has no isolated points, which has no isolated points, using Bayer's theorem, prove that X is uncountable. Our space X is uncountable. Now, solution. Assume contrary that, but first some solution. But first recall. X is complete plus X is union closed implies, and one more thing, interior. So this set does not need to be X, so E. Interior E is non-empty by Bayer theorem. Interior E M is non-empty for some n in natural numbers. Okay. So solution. Assume contrary that our space X is countable. I.e. we can write as X union M 1, 2. Sorry, let me pass the new page. I.e. we can write X is union 1 to infinity Xm, the 1 point sets. Clearly these are closed as call this En as 1 point set in metric space X. Closed sets. Clearly X is complete plus X equals to interior X, which is non-empty. X is metric space, X must be non-empty. So implies O and En is closed for all n. Implies by by Bayes' theorem, there exists some m natural numbers such that interior En is non-empty. Implies interior non-empty sum. Sorry. Okay, but this is what? Subset of 1 point z xm implies interior xm is xm. So implies there exists delta greater than 0 such that ball xm delta equals to xm. Therefore, xm is isolated point, but this is a contradiction. At the beginning in the question, we assume our space X has no isolated point, but by assuming X is countable, we conclude that xm is isolated point for some and xm is isolated point of X. It's a contradiction. Hence, our space X is uncountable. This is, I think, problem 6. Problem 7. Do you have any question about problem 6? No? Okay, let me continue. It is already done. So for each n is a natural number, let En given like this, psi in bounded sequence in natural numbers, bounded functions means bounded sequences, such that this is 0 for all I greater than n. Okay. Our question is this: prove that Em is closed in Bn by using Bayes' theorem. Prove that the set, each set has empty interior in Bn. Now, so Bayes' theorem is applicable as Bn is complete. After showing the En closed, then we will apply Bayes' theorem first. Solution. First, show this set is closed. As Bn set of bounded sequence is complete, implies En is closed if and only if En is complete. Okay. In fact, we will show that En is complete. Given any Cauchy sequence let's say ne demişim kısa K in EM implies this sequence is Cauchy in where our whole space to bound sequences, okay, but this set is complete, implies psi k converged psi in Bn. In fact, we will show that psi in here. So psi is what? We can write like this. Less than psi e minus psi e k plus. Okay. As psi k converges to psi, there exists k0 in so given epsilon greater than 0, any epsilon, as psi k converges to psi, there exists k0 in natural numbers such that for all k greater than k0, d sub psi k psi less than epsilon. Okay, come to previous page. So we have, okay, this is less than or equal to I psi e less than d sub psi k psi plus, but this is less than epsilon plus for all k greater than k0. So if E is greater than M, then psi ek is 0 implies 0. So for all I greater than M, we have psi e less than epsilon. For all epsilon greater than 0, then by epsilon lemma, psi e less than or equal to 0 implies. So implies psi e equals to 0 for all e greater than M, i.e. psi in so this set is complete, implies closed. The first part we are done. Now we will show that the E, now we will show that is empty. Claim interior E and EM is not empty for all that. But how? Well, assume let's so for all delta greater than 0 and for all psi in E, I psi is 0 for then so psi is psi 1, psi 2, psi here 0. Choose psi delta like this, psi 1, psi m, here the delta over 2. Then the sub psi bar or tilde is delta over 2 is delta implies ball psi tilde in this ball, but clearly it is not in EM, but EM. So from here, but let me write here. But clearly EM implies interior EM is empty for all m. So X is complete, this is given. X is what? So Bn is complete. Plus EM is closed for all m. Plus interior EM is empty for all m. Therefore, we have implies by Bayes' theorem. In fact, contrapositive of Bayes, interior E is empty. So we are done. Do you have any question? This is no problem 7. So let me pass the new page. Problem 8. This is the last question of this last recitation. For each n, let an be a dense open. Sorry, is not. Sorry, not this, but okay. Let this fi I and I be a set of continuous real valued functions defined on a complete matrix space X. Suppose for all X in X, the set is bounded. Prove that there exists a constant lambda greater than 0, and then open ball ball x0 r such that for all I in I and x in this ball, we have what? Oh, this inequality Fix less than or equal to lambda. Okay. Solution. Here we will use again Bayes' theorem, but how? So the set. So each set is bounded. The set for the set for all x in x, the set this set in E is bounded implies for all x in x there exists nx in natural numbers, maybe real numbers, but you may take the natural numbers such that n sub x. Okay. Now consider the set. Now consider the set. Here. Intersection Fi inverse this compact set. Inverse image to this compact set. So this is closed. This guy is closed as Fi continuous for all I. So this is continuous as arbitrary intersection. Okay. Now we can write how. So x can be written like this, union. Now I am writing x in x. E intersection E in E Fi inverse this set. This is e to the x, so we have union x in x, e to the x. But this may be uncountable union. Closed. So now we cannot apply Bayes' theorem. You need some countable union. But in fact, we can write this set x in x intersection I in I this set as union. Now m1 to infinity, check the space. It's the easy exercise. You may check it. Intersection I and I. So call this En. By similar arguments, as above, En is closed for all n. Okay? So X can be written like this. Closed. X is complete and clearly non-empty X. So interior X is X, which is non-empty, implies by Bayes' theorem, there exists n in n, in natural numbers, such that interior En is non-empty. Non-empty by Bayes' theorem. X is complete and can be written as a countable union of closed sets, and clearly its interior is non-empty. So one of the sets this closed set must has non-empty interiors by Bayes' theorem. So it implies interior of intersection I and I minus n, not minus n, is non-empty. So implies there exists x0 and x, in fact, and are greater than 0, such that both x0 are subset of En, which is of this set. Implies for all x in this ball, Fix for all I for all I and I. So Fix belongs to this closed set, but implies absolute value for all I and I. Absolute value of this less than or equal to n. So take lambda is n, then for all x in both x row r, and for all I and I, Fix is less than or equal to lambda. So we are done. Do you have any questions? No. So this is end of our today recitation. In fact, the last recitation. Now I am stopping the sharing and stopping the recording. Yes.